Power Electronics. Chapter 3. AC to DC Converters. Rectifiers. Outline 3.1 Single-phase controlled rectifier. 3.2 Three-phase controlled rectifier. 3.3 Effect of transformer leakage inductance on rectifier circuits. 3.4 Capacitor-filtered uncontrolled rectifier. 3.5 Harmonics and power factor of rectifier circuits. 3.6 High-power controlled rectifier. 3.7 Inverter mode operation of rectifier circuit. 3.8 Realization of phase control in rectifier circuits. 3.1 Single-phase controllable, rectifier. 3.1.1 Single-phase half-wave controlled rectifier. 3.1.2 Single-phase bridge fully controlled rectifier. 3.1.3 Single-phase full-wave controlled rectifier. 3.1.4 Single-phase bridge half-controlled rectifier. 3.1.1 Single-phase half-wave controlled rectifier. Resistive load. 3:1. Half-wave, single pulse. Triggering delay angle, firing angle. 3.1.1 Single-phase half-wave controlled rectifier. Inductive, resistor-inductor, load. Basic thought process of time domain analysis for power electronic circuits. The time domain behavior of a power electronic circuit is actually the combination of consecutive transients of the different linear circuits when the power semiconductor devices are in different states. 3:2. Omega t equals A, I dot D dot equals 0. 3:3. Single-phase half-wave controlled rectifier with freewheeling diode. Inductive load, L is large enough. Vd I A T U 1 2 L R D Vd 3:5 3:6 3:7 3:8 Maximum forward voltage, maximum reverse voltage. Disadvantages: only single pulse in one-line cycle. DC component and the transformer current. 3.1.2 Single-phase bridge fully controlled rectifier. Resistive load. D R T U 1 2 I A B Vd 3 4 A. For Thyristor, maximum forward voltage, maximum reverse voltage. Advantages: 2 pulses in one-line cycle. No DC component in the transformer current. 3.1.2 Single-phase bridge fully controlled rectifier. Resistive load. Average output, rectified, voltage, 3 to 9. Average output current, 3 to 10. For Thyristor, 3 to 11. 3 to 12. For transformer, 3 to 13. 3.1.2 Single-phase bridge fully controlled rectifier. Inductive load, L is large enough. 3 to 15. Commutation. Thyristor voltages and currents. Transformer current. Electro-motive-force, EMF, load. With resistor. Discontinuous current ID. Electro-motive-force, EMF, load. With resistor and inductor. When L is large enough, the output voltage and current waveforms are the same as ordinary inductive load. When L is at a critical value. 3 to 17. 3.1.3 Single-phase full-wave controlled rectifier. Transformer with center tap. Comparison with single-phase bridge fully controlled rectifier. 3.1.4 Single-phase bridge half-controlled rectifier. 2. VD. VD. I. D. T. 2. A. L. U. R. U. VD. D. 2. B. R. 3. 4. VD. VD. Half control. Comparison with fully controlled rectifier. Additional freewheeling diode. Another single-phase bridge half-controlled rectifier. Comparison with previous circuit. No need for additional freewheeling diode. Isolation is necessary between the drive circuits of the two thyristors. Summary of some important points in analysis. When analyzing a thyristor circuit, start from a diode circuit with the same topology. The behavior of the diode circuit is exactly the same as the thyristor circuit when firing angle is 0. A power electronic circuit can be considered as different linear circuits when the power semiconductor devices are in different states. The time domain behavior of the power electronic circuit is actually the combination of consecutive transients of the different linear circuits. Take different principle when dealing with different load. For resistive load, current waveform of the resistor is the same as the voltage waveform. For inductive load with a large inductor, the inductor current can be considered constant. 3.23 Phase controlled, controllable, rectifier. 3.2.13 Phase half-wave controlled rectifier. The basic circuit among three-phase rectifiers. 3.2.23 Phase bridge fully controlled rectifier. The most widely used circuit among three-phase rectifiers. 3.2.13 Phase half-wave controlled rectifier. Resistive load, A equals 0 degrees. Common cathode connection. Natural commutation point, resistive load, A equals 30 degrees. Resistive load, A equals 60 degrees. Resistive load, quantitative analysis. When a 30 degrees, load current ID is continuous. When a greater than 30 degrees, load current ID is discontinuous. 3 to 18. 3 to 19. Average load current. Thyristor voltages. 3 to 20. 1 resistor load, 2 inductor load. 3 resistor inductor load. Inductive load, L is large enough. Load current ID is always continuous. Thyristor voltage and currents, transformer current. 3 to 18. 3 to 23. 3 to 24. 3 to 25. 3.2.23 Phase bridge fully controlled rectifier. Circuit diagram. D. B. A. C. I. U. VD. 1. 3. 5. 4. 6. 2. T. N. Load. Common cathode group and common anode group of thyristors. Numbering of the 6 thyristors indicates the trigger sequence. Resistive load, A equals 0 degrees. Resistive load, A equals 30 degrees. Resistive load, A equals 60 degrees. Resistive load, A equals 90 degrees. Inductive load, A equals 0 degrees. Inductive load, A equals 30 degrees. Inductive load, A equals 90 degrees. Quantitative analysis. Average output voltage. For resistive load, when a greater than 60 degrees, Load current ID is discontinuous. Average output current, load current. Transformer current. Thyristor voltage and current. Same as three-phase half-wave rectifier. EMF load, L is large enough. All the same as inductive load except the calculation of average output current. 3 to 26. Electronics. 3 to 27. 3 to 20. Power. 3 to 28. 3 to 29. 31. 3.3 Effect of transformer leakage inductance on rectifier circuits. In practical, the transformer leakage inductance has to be taken into account. Commutation between thyristors thus cannot happen instantly, but with a commutation process. Commutation process analysis. Circulating current IC during commutation. Commutation angle. Output voltage during commutation. UA equals to middle dot pound middle dot dia slash dt. IC, 0 id. IA equals IC, id 0. ID equals IC, 0 id. 3 to 30. Quantitative calculation. Reduction of average output voltage due to the commutation process. Calculation of commutation angle. ID, G. XP, G. For a 90 O, A, G. 3 to 31. 3 to 36. Summary of the effect on rectifier circuits. Single-phase full wave. Single-phase bridge. Three-phase half wave. Three-phase bridge. Impulse rectifier. 1. 2. Circuits. Conclusions. Commutation process actually provides additional working states of the circuit. d/dt of the thyristor current is reduced. The average output voltage is reduced. Positive d/dt. Notching in the AC side voltage. 3.4 capacitor-filtered uncontrollable, rectifier. Emphasis of previous sections. Controlled rectifier, inductive load. Uncontrolled rectifier, diodes instead of thyristors. Wide applications of capacitor-filtered uncontrolled rectifier. AC-DC frequency converter. Uninterruptible power supply. Switching power supply. 3.4.1 capacitor-filtered single-phase uncontrolled rectifier. 3.4.2 capacitor-filtered three-phase uncontrolled rectifier. 3.4.1 capacitor-filtered single-phase uncontrolled rectifier. Single-phase bridge, RC load. 3.4.1 capacitor-filtered single-phase uncontrolled rectifier. Single-phase bridge, RLC load. 3.4.2 capacitor-filtered three-phase uncontrolled rectifier. Three-phase bridge, RC load. 3.4.2 capacitor-filtered three-phase uncontrolled rectifier. Three-phase bridge, RC load. Waveform when WRC 1.732. A WRC equals BWRC less than 3.4.2 capacitor-filtered three-phase uncontrolled rectifier. Three-phase bridge, RLC load. 3.5 Harmonics and power factor of rectifier circuits. Originating of harmonics and power factor issues in rectifier circuits. Harmonics, working in switching states, nonlinear. Power factor, firing delay angle causes phase delay. Harmful effects of harmonics and low power factor. Standards to limit harmonics and power factor. 3.5.1 Basic concepts of harmonics and reactive power. 3.5.2 AC side harmonics and power factor of controlled rectifiers with inductive load. 3.5.3 AC side harmonics and power factor of capacitor-filtered uncontrolled rectifiers. 3.5.4 Harmonic analysis of output voltage and current. 3.5.1 Basic concepts of harmonics and reactive power. For pure sinusoidal waveform. For periodic non-sinusoidal waveform. Or where. Fundamental component. Harmonic components, harmonics. 3 to 54. 3 to 55. 3 to 56. Harmonics-related specifications. Take current harmonics as examples. Content of nth harmonics. N is the effective, RMS, value of nth harmonics. I1 is the effective, RMS, value of fundamental component. Total harmonic distortion. E is the total effective, RMS, value of all of the harmonic components. 3 to 57. 3 to 58. Definition of power and power factor. For sinusoidal circuits. Active power. Reactive power. Q equals UI sinh. Apparent power. S equals U dot I. Power factor L equals cos J. 3 to 59. 3 to 61. 3 to 60. 3 to 63. 3 to 62. 3 to 64. Definition of power and power factor. For non-sinusoidal circuits. Active power. P equals UI1 cos 1. Power factor. Distortion factor, fundamental component factor. N equals I1, I. Displacement factor, power factor of fundamental component. L1 equals cos 1. Definition of reactive power is still in dispute. 3 to 65. 3 to 66. Review of the reactive power concept. The reactive power Q does not lead to net transmission of energy between the source and load. When Q superscript 10, the RMS current and apparent power are greater than the minimum amount necessary to transmit the average power P. Inductor, current lags voltage by 90 degrees, hence displacement factor is 0. The alternate storing and releasing of energy in an inductor leads to current flow and non-zero apparent power, but P equals 0. Just as resistors consume real, average, power P, inductors can be viewed as consumers of reactive power Q. Capacitor, current leads voltage by 90 degrees, hence displacement factor is 0. Capacitors supply reactive power Q. They are often placed in the utility power distribution system near inductive loads. If Q supplied by capacitor is equal to Q consumed by inductor, then the net current, flowing from the source into the capacitor-inductive load combination, is in phase with the voltage, leading to unity power factor and minimum RMS current magnitude. Electronics. Power. 47. 3.5.2 AC side harmonics and power factor of controlled rectifiers with inductive load. Single-phase bridge fully controlled rectifier. AC side current harmonics of single-phase bridge fully controlled rectifier with inductive load. 3 to 72. Where N equals 1,3,5. 3 to 73. Conclusions. Only odd-order harmonics exist. In 1/n. In A1 equals 1/n. Power factor of single-phase bridge fully controlled rectifier with inductive load. Distortion factor. Displacement factor. Power factor. 3 to 75. 3 to 76. 3 to 77. Three-phase bridge fully controlled rectifier. AC side current harmonics of three-phase bridge fully controlled rectifier with inductive load. 3 to 79. Where 3 to 80. Conclusions. Only 6 K1 order harmonics exist. K is positive integer. In 1/n. In A 1 equals 1/n. Power factor of 3-phase bridge fully controlled rectifier with inductive load. Distortion factor. Displacement factor. Power factor. 3:81. 3:82. 3:83. 3.5.3 AC side harmonics and power factor of capacitor-filtered uncontrolled rectifiers. Situation is a little complicated than rectifiers with inductive load. Some conclusions that are easy to remember. Only odd-order harmonics exist in single-phase circuit, and only 6K1, K is positive integer, order harmonics exist in three-phase circuit. Magnitude of harmonics decreases as harmonic order increases. Harmonics increases and power factor decreases as capacitor increases. Harmonics decreases and power factor increases as inductor increases. 3.5.4 Harmonic analysis of output voltage and current. 3:85. Where? 3:86. Output voltage of impulse. Rectifier when A equals 0 degrees. 3:87. Ripple factor in the output voltage. Output voltage ripple factor. Where R is the total RMS value of all the harmonic components in the output voltage, and U is the total RMS value of the output voltage. Ripple factors for rectifiers with different number of pulses. 3:88. 3:89. 2. 3. 6. 12. GU percent. 48.2. 18.27. 4.18. 0.994 Harmonics in the output current. 3:92. Where? 3:93. 3:94. 3:95. Conclusions for A equals 0 degrees. Only Mk, K is positive integer, order harmonics exist in the output voltage and current of impulse rectifiers. Magnitude of harmonics decreases as harmonic order increases when M is constant. The order number of the lowest harmonics increases as M increases. The corresponding magnitude of the lowest harmonics decreases accordingly. For a superscript 1 0 degrees. Quantitative harmonic analysis of output voltage and current is very complicated for a superscript 10 degrees. As an example, for three-phase bridge fully controlled rectifier 3:96, 3.6 high-power controlled rectifier 3.6.1 double-star controlled rectifier 3.6.2 connection of multiple rectifiers 3.6.1 double-star controlled rectifier. Circuit. Waveforms when A equals 0 degrees. Difference from 6-phase half-wave rectifier. Effect of interphase reactor, inductor, transformer. 3:97. 3:98. Quantitative analysis when A equals 0 degrees. 3:99. 3:100. 3:101. 3:102. Waveforms when A greater than 0 degrees. Comparison with three-phase half-wave rectifier and three-phase bridge rectifier. Voltage output capability. Same as three-phase half-wave rectifier. Half of three-phase bridge rectifier. Current output capability. Twice of three-phase half-wave rectifier. Twice of three-phase bridge rectifier. Applications. Low voltage and high current situations. 3.6.2 connection of multiple rectifiers. Electronics. Connection of multiple rectifiers. To increase the output capacity. To improve the AC side current waveform and DC side voltage waveform. Larger output voltage, series connection. Larger output current, parallel connection. Power, phase shift connection of multiple rectifiers. Parallel connection. 12-pulse rectifier realized by paralleled 3-phase bridge rectifiers. Phase shift connection of multiple rectifiers. Series connection. 12-pulse rectifier realized by series 3-phase bridge rectifiers. Quantitative analysis of 12-pulse rectifier. Voltage. Average output voltage. Parallel connection. Series connection. Output voltage harmonics. Only 12 meters harmonics exist. Input, AC side, current harmonics. Only 12K ±1 harmonics exist. Connection of more 3-phase bridge rectifiers. 3, 18-pulse rectifier, 20 degrees phase difference. 4, 24-pulse rectifier, 15 degrees phase difference. Sequential control of multiple series connected rectifiers. Circuit and waveforms of series connected. 3 single-phase bridge rectifiers. 3.7 inverter mode operation of rectifiers. Review of DC generator motor system. Should be avoided. Inverter mode operation of rectifiers. Rectifier and inverter mode operation of single-phase full-wave converter, necessary conditions for the inverter mode operation of controlled rectifiers. There must be DC EMF in the load and the direction of the DC EMF must be enabling current flow in thyristors. In other words, M must be negative if taking the ordinary output voltage direction as positive. A greater than 90 degrees so that the output voltage UD is also negative. Inverter mode operation of 3-phase bridge rectifier. Inversion angle, extinction angle. A plus equals 180 degrees. Inversion failure and minimum inversion angle. Possible reasons of inversion failures. Malfunction of triggering circuit. Failure in thyristors. Sudden dropout of AC source voltage. Insufficient margin for commutation of thyristors. Minimum inversion angle, extinction angle. B mine equals D plus G plus Q, 3 to 109. 3.8 Realization of phase control in rectifier circuits. Object. How to timely generate triggering pulses with adjustable phase delay angle. Constitution. Synchronous circuit. Sawtooth ramp generating and phase shifting. Pulse generating. Integrated gate triggering control circuits are very widely used in practice. A typical gate triggering control circuit. Waveforms of the typical gate triggering control circuit. Electronics. Power. 78.